Hi, I'm Einar. Welcome to this talk on functional programming and fish. My day job, my day job is working on this, which is NRK TV, which is like the national public broadcaster in Norway, so doing TV streaming. But this talk is not about that. It's about functional programming and art. And in particular, it is about trying to reconstruct something that looks like this using functional programming. And that seems like a daunting task, so luckily someone's done all the hard thinking for me. So in 1982, Peter Henderson wrote a paper called Functional Geometry, where he shows how to decompose and reconstruct something that looks like Escher's square limit using functional programming. So the idea of this talk is to try to do the same thing using Elm. Yes, so we have here a fish, and this is, it's sort of my reconstruction of this fish that you can see in Henderson's paper. The sort of interesting thing, I think at least, about this fish and Henderson's paper is that in the paper, Henderson defines a picture not as sort of a collection of pixels, but rather as a function from some sort of bounding box to some sort of rendering. And in Elm, that looks like this, right? So a picture is a function from some box to some rendering. And in practice, in this talk, that rendering will then be turned into an SVG in the browser. And the rendering, there's nothing particularly interesting about that. It's a bunch of shapes with some styling applied to it, not that much styling, but it gives us some possibility to control colors and stuff like that. A very simple picture is the blank picture, which is a function that takes whatever and returns, a list of nothing, which is a sort of degenerate rendering, if you like. It's more useful than you'd think. Now this bounding box is just 3 vectors, so like A, B, and C vector. I'm going to show you, we started with this picture. So I can sort of draw my bounding box if I like, and that sort of hopefully helps to understand what's going on. So this is now my box. This is my A vector, my B vector, and my C vector going up like that. And that sort of defines the space that's available for my fish. Now we started with a fish, but I think just like in the paper, Henderson shows sort of basic transformations on this letter F. So let's try to do the same thing. So I have a different picture, which is not a fish. So now I have my F in here. And the interesting thing about having this box that I can manipulate is that I can manipulate the box. So I can...
Can we ask questions?
Yeah, sure. Okay.
Can I ask a question?
Yeah.
What is the meaning of the triangle between box and F in render? The triangle.
Oh, this one. Oh, I'm sorry. This is sort of a ligature. So it's composed 2 symbols. It's a pipe and...
Function composition?
No, it's a pipe forward. So basically, when I write box pipe forward like this is the same thing as calling the function f with box as a parameter. Right, so it's just a way of sort of inverting the order. So I'm starting with the argument to the function and then sort of piping it into my function instead of writing the function name first and then. So that would be similar like in something like that.
Show it like a process.
Yes. So it's like a process, yes. So I'm doing that now twice. So I'm first piping my box to my f, and then I'm piping whatever that produces to my rendering function. Yes, so I can shorten my B vector, for instance, and what happens then is that my image sort of has to adapt, right? And I can, well, do sort of more or less weird things to it. And what's interesting with that is that I can exploit this to do transformations on my picture. So the first transformation I'm going to try to do is turning the picture like 90 degrees, like that. Yes, I'm gonna have my old box first, so that I don't mess up. Yes, so let's see. So I have an outline here. So default implementation is to return the blank picture. So in Elm, what I do here is I sort of describe my function signature. This is going to accept a picture and produce another picture. And this is now my picture, and this is my return value. Now, since a picture is just another function, so a function from a box to some rendering, I can return this as, well, this is Elm's lambda syntax. So I'm introducing a function here, which takes one parameter called box. And then I'm going to call my picture, because it's a function, so I can give it a box and produce a rendering. So the trick I'm going to try to do is, okay, I'm going to use my old picture, but just before, instead of giving it my box directly, I'm going to turn the box and then give it to the picture. Let's see. Well, I don't have the turn box function yet. Let's see, turn box. Now, more Elm here. The purpose of this talk is not to teach you Elm, but it's to show you how I use Elm. I think there's a workshop on Elm tomorrow if you're interested in learning more, like how to properly program Elm. So what I'm doing here is, in Elm you can deconstruct sort of like a record type directly in the function signature. So this is my box, but I'm decomposing it into A, B, and Z. And then I can do stuff with it. And the box now consists of vectors. And vectors are just like X and Y coordinates. And I have functions to like add vectors, subtract vectors, and stuff like that. So I can now, the idea is to sort of, if I turn the box, then the picture will have to follow along. So I'm going to move this arrow over here, and I'm going to have my green arrow is going to go like that, and my new blue arrow is going to go up like that. So the way to do that is, okay, I add my old A and B. That should take me there, which is where I want to go. And my new B vector is going to be the old Z vector, which is the one pointing up. And then finally, for my C vector, that's going to be the B vector, but going in the other direction. So now, hopefully, let's see if I call my turn. And I'm going to show the turned box as well. Right, like that, yes. Now, in Elm, you can also do function composition, and that's going to make things a little bit easier for us. Because whenever you have a function that goes from A to B, like say you have an f that goes from A to B, and maybe you have a function g that goes from B to C, then you can sort of glue those together. You can take the output from here and pass it in there and create a new function that goes from A to C. Like that. And the way you do that in Elm is by saying, okay, I'm going to compose them, which says, okay, call this first and then do whatever G does. And we can do that here. And we have a picture, which is a function from a box to a rendering. And we have this turn box thing, which is a function from a box to a box. Oh, well, yes, like that. So now I can sort of glue these together. I can take whatever this outputs and weld it together with that. If I do that, I end up with this. So basically just putting this turn box adapter in front of my original picture. Yes. And I can do more, because what's kind of interesting with these, like box to box and picture to picture, is that you can compose them with themselves, right? So I can create a like turn twice function just by composing turn with itself. So I'm going to create like a generic way to do that, which is called times, which is going to compose some function from A to A with itself n times. So sort of in the degenerate case, if n is less than 1, then I'm just going to do a return identity, which means whatever value you give me, I'm going to give you the same value back. But if n is greater than, or at least 1, then I'm going to compose the function with calling times recursively with itself. So it's sort of self-composing these A to A functions. And to sort of demonstrate how that works now, I should be able to do like that, yes. So I can do this an arbitrary number of times. And of course, if I do the fourth time, that's just going to be the same as, well, not doing it at all. So in this case, I'm turning the f 0 times, right? Which is nothing, basically. So that was a lot of talk about the first picture transformation, and we're not too close to Escher yet, but we will get there. So the next transformation in Henderson's paper is called flip. And the idea of flip is that you basically take this, if you think of this as being drawn left to right, it's going to draw the same picture right to left. Or you can think of it as a mirror or something like that. So I'm going to try to flip my F letter. And like before, I'm going to show this this flipped box as well. So let's see, yeah. So flip. I can do exactly the same thing. So I'm just going to use like a flip adapter in front of my original picture. And then, well, for flipping, it's even easier than before. What I need to do is just to, like before, I'm going to move this over there, then I'm going to turn this the other way around, and I'm done. So add A and B together, negate B, and that's flip box. Yeah, like that. Now, if I do this multiple times, I'm just going to flip back and forth with the same original picture. Next transformation is slightly more interesting and a little bit more sort of into, or we're going to define it because we're going to need it for this particulars of this Escher picture. And that's in Henderson's paper, it's called rot 45 because it's sort of rotated 45 degrees, but you also shrink it. And I think it looks like sort of throwing the picture up into the air, so I call it toss instead. We're going to use the same thing here. Okay, I can have my outline. Compose tossbox. Now, tossbox is a little bit, there's a little bit more sort of vector manipulation going on, but it's not too bad. And also, don't feel bad if sort of the details of the vector manipulation is like, oh, I don't know why he did that or whatever. It doesn't really matter. So I'm going to start at A, which my original A, which points there, and I'm going to move it somewhere else. Let's see. Now I have a function to scale vectors, so I can sort of shrink it by half. And this is, well, this is where I want to go. And I'll show you where that ends up. Oh, let's see. And yeah, I think maybe it helps. I can sort of draw an arbitrary number of boxes in here if I like. So I'm going to show the original box and the sort of the tossed box. So this is what's going on, right? So I'm throwing my picture up into the air, and I want to go, well, from A and then to sort of midway between B and C, right? And you could go on, obviously. So you can toss your box, or you can toss your picture multiple times if you like. And you'd go like that. Actually, I think I'm just going to gather up all my intermediate tossed boxes so we sort of see what's going on in detail. Again, if n is less than 1, I'm just going to return my original box. Otherwise, I'm going to sort of keep my box and then add that to calling this tossed box recursively. So tossed box is n minus 1 and the tossed box. So I'm sort of now passing ever more tossed boxes into itself. And the effect of that, so tossed boxes, let's see. If I have a number like 3, let's see if this works. Yeah, so now we can sort of see the intermediate boxes as we go along. And it creates this, well, I should have used my n here, right? And it creates this sort of nice rotating effect. Okay, so that was the final sort of simple transformation, I guess. Now we're going to try to compose pictures into more complex pictures, so taking more than one picture and composing them together. So the first one is going to be a function called above. So I'm going to try to draw now one picture on top of the other, basically. And how do I do that? Well, so I have my above outline. So I'm going to take two pictures and produce a final picture, which is the composed picture. But I want to do that in sort of a generalized way so that I can assign a weight to each picture. So it doesn't have to be sort of like evenly split. So I'm going to say, okay, maybe I want more space for my first picture than my second picture, or the other way around. And if I give them equal weights, that's going to give them like 50-50, right? So this is a little bit more stuff to do. But every picture now is a function from a box to a rendering. So I'm going to start with the box. And the idea here is to basically create two boxes, one for the top picture and one for the other picture, using my original box. I'm going to split the box in half and then sort of combine the results. First thing I'm doing is to calculate the fraction given to the top picture just from those two weights. But then I'm going to sort of split my box into a top box and a bottom box. See, like that. And then when I have those boxes, I'm just going to pass them to my pictures, right? So the first picture is going to get its top box, and then the second picture is going to get its second box. And the way to, well, these are just going to produce basically lists, because renderings are lists of stuff, like this list of shapes. So I can compose those in Elm using this plus plus thing, which is like, okay, I have two lists, I want to combine them to a single list, then it's plus plus. Of course, I don't have split vertically yet, so let's work on that. So I'm going to split vertically. Given some sort of fraction given to the top box, I'm going to split one box into two boxes. And yeah. So my top box, the way I'm going to do that is I'm going to have to move that one upwards, right? So you can't start at the same spot. So that, how far am I going to move it? Well, I have this fraction f, and I'm going to move it above whatever place I have left for the bottom picture, so that's going to be 1 minus f. And then I'm going to have to sort of shrink it vertically, right? So scale it, basically, with this fraction f. And again, you can see this pipe thing. So this, what happens here is I'm going to, well, move it vertically, which is like, okay, calling this function with the box, and then whatever that produces, it's going to be passed to this one. Not. A little bit simpler for the bottom one. I don't have to move that, so I'm just going to scale it with whatever space I have for the bottom one. Like so. Now I have, well, still more helper functions to write, but they're not too difficult. So again, I'm decomposing this box, and I have my fraction f. So moving is just about moving the a vector, right? So which says where you start. So you add to this. So you move along the sort of the c vector, which is the one going vertically. And that's all you have to do for moving. Scaling is also quite simple. You just have to sort of shrink the c vector a bit. Let's see. Is that all? I think that's all. I just have to call it here in my above function. So I can do like this, which gives me even weights. Or I can use this thing called partial application, which says, okay, I'm going to give 2 of my arguments to this above ratio function. Then what I'm going to be left with is a function that still expects 2 pictures to produce the final picture. Let's see if that works. And maybe we should, I think, so top and bottom again. So split vertically in half my original box. Yeah. So now we have the top picture is going to be the original f, and then the bottom picture is going to be the turned f, right? And of course, I can, if I like to, I can compose this further like this. So maybe I want to turn it twice. And what would happen then? So B1, B2. So if I split again, so I get something like this, right? I can keep going. Now, if I wanted even spacing here, because this is not evenly spaced, right? Then I have to use this above ratio function. So I can do so now I'm allocating a third of the space to the top, to the first picture, right? So now I have evenly spacing. Yes. Now, the second sort of composition function we're going to use is called beside, and it's very similar to above, so I'm going to cheat a little bit to sort of speed up. So let's see, cheat, beside, well. So basically all I'm doing is the same process, but going the other direction. So not too interesting to watch the details of that. So let's just do cheating for the split horizontally. And so now I'm just adding exactly the same thing, but going in the other direction like this. So let's see. So maybe I do side and yeah, something like this, right? So now I can put pictures next to each other as well, which is cool. And now we have, it might not seem like it, but we've come quite far. So now we can largely leave this low-level vector box manipulation stuff behind, and we can start to use these building blocks that we have to create more interesting functions. And the first one we're going to try to create is called a quartet, which creates like a 2x2 grid from 4 pictures. So we combine 4 pictures into a single picture. And you know, having seen all of this, especially if you're not familiar with Elm or something that looks like Elm, this can be a bit daunting. But you'll see that once we have those, we can create quite simple functions now. So all I need to do to create a quartet is to combine. So I'm calling these now my northwest pictures, my northeast picture, and so forth. So if I combine the two northern pictures and the two southern pictures and put them above each other, then we're going to have our quartet. So let's try. I have another picture here called George, which is like a stick figure, and I'm going to show him to you. Yeah. So this is George, and I think maybe we're ready to sort of leave these lines behind. We can just drop them. And I like to create sort of a simple artwork from George. So now I have 4 instances of George, so this is the same as I had before. But I can do stuff. Like I can flip him and turn him twice over. And then he sort of starts holding hands with himself, which is. And I can turn this one a couple of times over. Now he fits with his legs. And now all we need to do is do something about this last one. And sort of the interesting thing about this exercise, I think, is how these pictures now start to compose quite freely. So it doesn't really matter that I flipped and turned stuff for the quartet. All it does, it takes 4 pictures, creates this grid. And I can, do more sort of like arbitrary stuff. So I'm creating another function called Q, which just takes a picture P and creates a quartet with 4 copies of it. Why would I want to do something like that? Well, I can start sort of build, arbitrarily large combinations of this. And, I think that's pretty cool, and you can throw it up into the air if you like. Quite free. And yes, that was quartet. Let's see. Next one is called NoNet, which is the same thing as a quartet, only a 3x3 grid instead of a 2x2 grid. That's also basically follows the same idea. But now we're sort of having to, instead of combining 2 pictures like that, we have to combine 3. So I'm going to create some helper functions. One is going to create sort of a row of pictures from 3 pictures and squish them together. And I want that evenly spaced, as we saw before. And then, first my western picture, and then combining the middle picture and the eastern picture. Similarly for column. Like so. Let's see. Whoa. And yeah, I'm going to drop these now. And yes, I want to import some more pictures, or some more letters actually. So let's see, I'm going to have an H and an E. Like so. So I have sort of these like basic shapes defined that I then turn into this sort of magic stretching pictures. Yeah. So now I'm going to create a NoNet out of these letters. It's going to look like this. And again, this is a NoNet is just a picture, and it accepts pictures as input. So you could create something like a zoom effect if you do something like that. So you can sort of imagine you're sort of going into infinity there, if you like. Yeah, that's the no-net, and the no-net is going to be the basic structure we use to sort of create this final square limit image that we're going to get to soon. So we had this sort of long detour without any fish, and I said there would be fish, and there was an image of a fish. So let's return to the fish, I suppose. So we have my fish. And I'm going to create one more sort of simple combination of pictures called over. And over takes two pictures and draws them inside the same box, which could get messy, right? So I'm going to create over. I don't have over yet. So over is in some sense similar to above, because it takes two pictures and sort of combines the results, but it doesn't create these individual boxes, it just uses the same box. So the way to do that is, well, basically, you just have to call each function with the box and combine the results. And, well, so what happens if I draw a fish on top of a fish? Well, it's just a fish, because now I have two identical fish on top of each other, or at least that's what I claim I have. If I combine it with an F, you can see that it looks ugly. If I combine it with the fish turned 2 times over, it looks nice, because Escher created sort of the structure of this fish. And he wanted them to sort of fit nicely within with itself, basically. So that's over. Now we're going to sort of try to start building up these tiles we need for the square limit. The first one is called T-tile. I don't know why it's called T-tile. It says T-tile in the papers. I'm calling it T-tile. It's not really explained in the paper. The paper is really super readable, by the way, so I recommend reading it. So now, obviously it doesn't have to be a fish, but it mostly makes sense if you pass it a fish picture. So it is a picture. It will work with any picture, but I'm calling it a fish. I'm going to create some sort of derivative fish from the original fish. So this means sort of, this is going to be my northern fish. That's what the N means. And I'm going to have an eastern fish as well, which is the northern fish turned 3 times. And then I'm going to put all of these together in the same picture. So all on top of each other with the original fish as well. And that will look ugly for most pictures, but not for the fish. So let's try. T-tile, fish. Yeah. So apparently a lot of thought was given to the shape of this fish. So that's one sort of building block we're going to use. Another building block we're going to use is called the U-tile. And again, I don't know why it's called the U-tile. And it's sort of similar to what the T-tile is. But now I'm also going to have a western fish and a southern fish. And an eastern fish again. And yeah, I'm just going to put all of these again on top of each other. Over fish. But I'm going to ignore now the original fish. So that's being left out and basically replaced by these 2 other fish. So let's try that. U-tile. And yeah, so basically I took the big fish and replaced it with 2 smaller fish. And, well, I don't know if you can see it, but that's actually going to be like the centerpiece here, right? So now we're getting somewhere. What we don't have yet are these sides and these corners. So that's what's coming next. And then we're going to have to do recursion, because, well, for obvious reasons, I guess. So I'm going to create a function called side. And that's going to be called with some number that determines how many recursive calls I'm going to do. So side, well, what's side going to look like? Side, well, it's going to take the n and the picture and then produce some sort of recursive thing. In the sort of degenerate case, I'm going to return the blank picture, so nothing, which is the easy part. The recursive case, I'm going to call side again recursively, shrinking my n so that eventually I'll reach the blank. And I'm going to have a t-tile as well. And then I'm going to compose those using my quartet. And I'm going to have 2 copies of calling this recursively. And then I'm going to have a turned t-tile and the t-tile as it is. Now, yeah, let's try it. So I want the boxes again now, so sort of to illustrate what's going on. And I think actually I'm going to, this could get cluttered. Well, this is the degenerate case, and I'm drawing a blank inside my box. Now what happens if I increase this one? It's going to be a quartet, so it should be now 4 pictures of something, right? This is my 2x2 grid. Yeah, but it's not perhaps clear because we don't really see the boxes, right? But this is basically my t-tile and my turn t-tile and 2 blanks. But I'm going to try to show what's going on with the boxes. So I have, again, a function that helps me sort of gather up the boxes that are produced by the recursive calls. And I think I'm going to have a slightly toned down visualization of the boxes. So let's see, and then I'm going to have to call this side boxes thing. Side boxes. So now we can see what's going on. So it's going to produce 4 boxes, and now we have 2 blanks. Now calling things recursively, if you recall, it's going to create sort of copies of whatever I have here, put up here and there, right? So you can see that it sort of proceeds making more copies of the basic shape into these blanks. So it sort of fills out the blanks with this side 1 thing as we proceed. And if I go far, you can see that I sort of approach the limit of my original bounding box. Okay, so that was side. Now we need something called corner. And once we have that, we're practically done. So it's quite similar in some sense. It's, again, a recursive thing. And I'm calling the corner function recursively. And I'm also calling the side function recursively. And you'll see why when I sort of try to demonstrate the same thing again. So this is another quartet. Northwestern thing is going to be the corner. And then it's going to be a side, and then a turned side. And then finally this U-tile thing, which is the one with the 4 fish. So let's try that. I'm going to do the same trick with the boxes so we can see what's going on. And that's using another helper function as well, just to gather up all the boxes. So, corner, and let's see, corner boxes. Yeah, well, again, blank for the degenerate case. Here we have our first sort of interesting thing where we have the U-tile. And then what we're going to do is, here I'm going to put sides. Here I'm going to put turned sides, and here I'm going to put basically copies of this one. So when I increase it, you can see that it sort of grows. And you can go on as long as you like. The browser will start to complain at some point because the SVG gets large, but apart from that, it should be fine. Okay, so now we have these things. So now we have all our building blocks for the square limit. So I'm going to create, well, the square limit is going to be a no-net. So I'm going to have to create a bunch of pictures. Northwestern thing is going to be the corner. Southwestern is going to be the northwestern corner turned. Let's see, yes. I can keep going like that. Yes. Now, north middle thing is going to be the side. And, well, I can get all the pieces I need just by turning each once around. And then finally for the middle one, that was the U-tile. And now, let's see. Typing is hard. Yeah, I'm going to drop these now. Let's see. 4 is nice. 5 and my browser gets slow. Yeah. So. Okay, so this is nice, but I think we still have like 5 minutes. Well, we sort of reproduce this, right? But there is, well, let's see. I can't really find it. Where is it? Yeah, this one has colors, right? So I have a different kind of project. Yeah, I don't think you can read it, but it says recursive fish in color. So this is essentially the same thing, but what I did is, in addition to the box, I have something called a lens. It's not a functional programming lens, but it's a box with a tinted color. So I add something called a hue, which could be blackish, grayish, or whitish, which gives me sort of 3 colors of fish. And yeah, when I have that, let's see, do I have it running? I think I have it running. Yeah, so now this is another version of the fish. This is the blackish version. I can re-hue it, or I thought I could, but I can't spell, so. And that sort of changes the color. It's the same fish, but it's, well, I can do it twice. Then I have a white fish, and I can presumably do it 3 times, and then I have a black fish again. So it sort of rotates like that. And with that, I can create sort of the final version of the square limit using these pretty colored fish. And it looks like this. Yes.
That's beautiful.
So. And of course, this is again just another picture. So, well, you know, if I wanted to, I can change its color, because that's sort of the important lesson is that it's still just a picture, right? And I can pose it, I can create a quartet of it, I can create a square limit of the square limit. That's going to make my browser kneel, but it works. So thank you. Any questions?
That's a lot of code.
Actually, for sort of the
Did you factor it at a point in time?
this, like, it's a bit of code, but it's not that much. I mean, basically, the combinators in Henderson's paper are 13 functions, and there are some helper functions, and of course, there is some sort of like stuff to turn this into SVGs and stuff that I haven't shown you. there's a bunch of stuff here. If you like, yeah, that's a point. Well, I'm not going to print it. Well, I have printed it on high resolution paper. It's quite nice. But well, there's a repo for this talk. So if you want to look at the code, there is also, if you're interested, I have created a workshop version that you can sort of walk through on your own if you're interested. So it's supposed to be self-contained, so you should be able to work through it. If not, feel free to ping me on Twitter or something like that with a question. So it should be entirely possible to sort of work through.
Did you try other patterns?
I have tried some other patterns, some other Escher patterns as well. Yeah, I have some with the birds and stuff like that. This is interesting because it has this sort of shrinking quality that I like. Yes. Okay, thank you.